Okay, we are rolling. Thanks again, everyone, for joining us. My name is John Sosa, the inventor and principal developer of MIPAR image analysis software. This is our third webinar that we've held, session number 2. This webinar is being recorded, both video and audio, so you should hear my voice clearly along with any questions that are asked during the session, and I'll be sure to repeat those if they're asked just to make sure they get on tape. We're going to be covering a general overview of MIPAR software, basic and advanced segmentation use cases. That'll take us into how we can take measurements from those features that are detected, how we can visualize those measurements, both as a spreadsheet, of course, but also by color coding features according to measurements, which is a somewhat unique but quite powerful feature in MIPAR. Batch processing multiple images with a developed segmentation recipe, and then reviewing that batch and extracting bulk measurements. And if anyone's interested at the end, we'll hit some 3D analysis. So you're looking at MIPAR's launch bar at a top and the status bar down below. If you are not running the 3D extension, anyone who's running a trial license will be running the 3D extension. Those of you that have purchased and have not purchased the 3D extension will just see 4 applications: the image processor, batch, real-time, and processed image editor. I'm running version 1.02 that was released yesterday, and I'm going to go in here first and just show you around the different applications. Again, feel free to speak up during the webinar, ask any questions that you like, connect your mic, and jump in anytime. I want this to be as live and interactive as it can be. I also apologize in advance for any slight performance degradation. We are running both. Okay, someone's mentioning they don't see my screen anymore. That's interesting. Let me fix that. Sorry. Okay. So let's do that. It looks like someone had jumped in with a screen share and disrupted mine. That's okay. Okay, great. Thank you very much. Appreciate the heads up. All right. So because we're screen recording and broadcasting live, this computer this workstation rather is taking a little bit of a beating, but it seemed to hold up pretty well yesterday, so we should be good. This is the image processor. This is MIPAR's most commonly used application. It's where single images are opened and processed. It's where recipes are built, our core technology. It's where recipes are loaded. It's where images are colored according to measurements. It's really the primary application. So you've got your menu bar atop, of course, file, actions, launching the other applications, your help menu that gives you direct access to our new user manual. Click that from any application and you'll be taken to the relevant page in the user manual. This is our user manual is entirely online, so it is going to be updated frequently. And however, if you are on an offline PC and need access to it, you're welcome to visit it from an online PC, download the entire thing as a PDF, and move that over to your offline PC. I know some of you might have air-gapped PCs and other things that you're working on. So then we move into our processing functions. We'll review these in more detail, or at least those that we make use of today. But here are your basic cropping, resizing, rotating, sort of your dimensional manipulation operations, your grayscale intensity manipulation functions here that are usually done prior to any sort of feature detection steps that usually make those steps easier to operate. Segmentation menu has your initial feature detection steps, different thresholds, region growing, active contour or snakes, local maxima and minima functions. Some more advanced tools for detecting edges, highlighting lines, finding circles, our new facial feature finding tool. I don't think we'll really have time to get into the pattern mapping, but that can be quite powerful. Morphology are your first manipulation steps of your your rough feature detection, eroding and dilating, separating features, smoothing them, making skeletons, replacing objects with equivalent shapes. In your cleanup menu, you have our beloved reject features tool that is quite commonly used in any recipe, and it lets you select or reject features from your selection based on their being above or below any number of different parameters. You'll see that in action for sure. Memory menu, where you put steps in and out of memory to both recall them later in the recipe, but also make use of them in steps that allow you to call another image. For example, the adaptive threshold allows you to use a black and white step, a memory step, as a mask in the thresholding. So those memory steps are set and recalled in this menu. Math operations for performing operations between two images, typically whatever is the current image in the recipe and the last set companion image in the recipe. So any step that you see with an asterisk means that it requires at least one companion image to be set at some point prior up in the recipe from where you currently are. Here are your global measurements that make one measurement per image. Your feature measurements give you a measurement per feature. This lets you colorize those features by those measurements, and here you can make measurements per pixel, things like a local thickness map or an area fraction map. We'll get into that when we talk about measurements. Your shortcut bar for your commonly used actions: opening images, loading recipes, saving images, saving recipes, adding a manual edit step in the recipe to manually select or reject features, measuring features, coloring, and local measurements. Interactive image tools: distance measuring, angle measuring, line profile, individual feature measurements, zooming and panning. Here's where you set your scale or your calibration factor so that you can measure things in units other than pixels. Simple image properties help on whatever preview window is open or whatever step is shown in the recipe. Hi, Maria. Okay.
Bárbaro.
Maria,
La llaman un ratito.
Maria, I'm not sure
Sí,
you know
sí,
we
sí,
can
sí,
hear
claro,
you.
Claro. Bárbaro. Sí. Gracias, Bessie.
Okay. Okay. So I'll just keep flipping through the apps here. We'll move quickly through the batch processor. This is where you will take a recipe that you've made, choose a bunch of images to crunch on, where you want the output to be saved. Here are some other options that we're not going to really use today. If you don't have the 3D extension, you won't see this bottom row. This is used for making 3D stacks and reconstruction files in MIPAR. The real-time processor is a cousin of the batch processor and looks very similar to this. It only differs in that instead of taking a set of images to crunch on, it monitors a folder, and every time a new image is added to the folder, it executes the recipe. So in principle, you could have a data server that your microscope is saving to, and every time a new image is saved to that folder, the recipe will execute. This is our least commonly used app, but it is there for special applications. The processed image editor is, again, your batch review application. So here's where you'll take your processed results, the corresponding reference images. You can flip through each one to see how the recipe did, make manual edits if you need to, open an image directly back into the image processor to redo a recipe. Because you read images directly off of the hard drive from this application, once you redo a recipe in here and you resave the processed image, then it'll automatically be updated in here. Well, you do have to click refresh, but it doesn't require any kind of reloading or anything. So there is communication between apps. Generating bulk measurements here for bulk global measurements for all the processed images, and feature measurements for getting measurements per feature from every image. We've got a question from Yesun, if I'm pronouncing that right. He asked about the supported file types. That's a great question. With regards to 2D file types, we have in our user manual a supported formats section. Natively, we support all the basic ones, and with the bioformats library, we add an additional 140 supported formats, including proprietary ones. This only requires that you download the bioformats Java package and drag it into the plugins directory in your MIPAR installation directory, and you'll then be able to open any format. In principle, I've not tested each one of these, unfortunately, but in principle, any format that's listed here, we support as a 2D image. As a 3D format type, you'll notice that right now, the way to get 3D data into MIPAR is to run a set of 2D images through the batch processor that turns, then if you check off 3D reconstruction or stack, turns it into either an image stack, MIPAR image stack format, or MIPAR reconstruction format that then gets opened in the 3D toolbox. So we are working on adding more direct import of existing 3D files like DICOMs and OIFs and AMs directly in the 3D toolbox, but right now we do not support that. You'll need your data to be a set of 2D image files that you then turn into a MIPAR stack or reconstruction through the batch processor. So I think that's a pretty good overview of the structure and the layout. We can jump right into some basic segmentation that should give us a better understanding of our principal application, the image processor. So we're going to start with a pretty simple example here. I've got a common material science example here. Particles in a matrix. I think it's some kind of composite. But MIPAR is quite flexible. We designed it for material science, but since its launch, folks have used it for anything from food science all the way to atomic imaging, all the way to satellite imaging. At the end of the day, an image is an image, and as long as you have some kind of contrast between what you care about and what you don't, we can likely, or you can likely, make a recipe that finds those features of interest. It doesn't always have to be intensity contrast. You can have pattern contrast. You could have a patch of atoms that are in one structure in one area and a different structure in another, and that is contrast of some sort, and MIPAR usually can pick it up. So this could just as easily be pepperoni on a pizza or trees in an aerial photograph. As long as there's something that identifies the difference between your features of interest and everything else, we can work with it. Let me also point out our recipe store that's on our website. If you have not visited that yet, I encourage you to. It is called a store, but it's always free. It's an ever-growing repository of recipes that we have built for various use cases. In the best of worlds, you can take one of these recipes and run it on your image and get the desired results. At the very least, though, it should be a good starting point for you to show you what a potential recipe would be for your problem. You can download these images as well as their recipes to expedite your MIPAR learning. We've got about 30 to 40 up there right now, and we will be adding those continually. So thanks to anyone who is willing to let us use images on our recipe store. We've got different sections here. We've got a metal section, biological, cell finding, colony finding for bacterial analysis, plants, more cells, wound healing, bacterial colony counting, all sorts of bio applications. And then some other composites examples. So feel free to browse this and definitely keep up to date with it. Also, as part of an annual license, we offer custom recipe building. So if you don't see one that fits your needs, or one of these needs more tinkering than you're willing to put in yourself, just ask for your own recipe. Send us an image if you can, tell us what it is you care about, and we'll try to get you a recipe back that works for you ASAP. We can also exchange recipes. Go ahead and just send us one that you're working on. We'll make some tweaks and send it right back. It's a information exchange that really no other software can offer, and it's been a huge value add to MIPAR, as many of our users have told us. So let me get started with an image here. To open an image, it's pretty simple. You've got three options: either File, Open Image, Open Image. Both of those do the same thing. You pick the file, or even easier, drag in your image. So we're going to start here. Let me show you first the recipe that I've built already. This is one that's up on the store. Again, to load a recipe now, you can either File, Load Recipe, I think Control L is the shortcut, or click Load Recipe and grab it, or again, you can just drag it in. So it's run through the steps that we've built, and at the end it shows you the different detected feature types. So we've got the matrix in blue and the grains in red. This is a completely non-destructive sequence, so you can double-click and look at any of these steps. We started with a threshold to find the background. Let me mention that you've got different viewing modes for each of these steps. So any step that is a black and white image, that's really what this image is in the back end, is a black and white image, and you can see that by going to black and white mode. So black is what you've selected at this point in the recipe, white is everything else, and you can also then show that as an overlay of the selection on the reference, as an outline, as a label map where the different colors represent the different features. This is all one feature here. It's all yellow because the matrix is all connected. And we can view any of these steps. So here we've started with a threshold. We've done some noise cleaning to get rid of the selected noise. We've done some cleaning within the noise. Then we've rejected some very small selection artifacts that were up in here. See those? Then we've inverted so that we've now selected the other phase, the particles. We went and did some memory operations just to avoid separating, so that we only targeted the larger features. So we put this one in memory, or store image 1. We went and we only kept the smaller ones, and we then set those in the companion memory slot. Then we went back to restore image 1 and did a separate features, and that went and made separation cuts along artificial joints like this. And then I only did that memory dance because sometimes the separate features can do some funny things to the really small ones. As you noticed, these guys got clipped in strange places, but we have those small features preserved in their pre-separation state right in here. So then just running a merge darker pixels will take all of the, I call them darker pixels because, again, they're black in the black and white view. So it takes all of the black pixels in this image and all the black pixels in your last companion image and adds them together. So you go from this to this. And then we invert just so we have the matrix finally cleaned up. Now, what I did was to set layers on each of these. I set each of these last steps as a layer, which tells MIPAR that they're important recipe steps, and they can then be overlaid together with different colors. So when you switch into layers view now, which is available if you have layers set, you can see color-coded to each step the different feature types that you've selected. This gives you a couple other advantages. Any measurements that you make can get, when you're in layers view and you make any measurements, say area fraction, that gets performed on both layers that you have set. So there we get an area fraction of the grains and the matrix. If you were just looking at one image, any of these, whatever image you're looking at, you can play area fraction. That'll just measure the area fraction of that one image. But with layers set, then you can measure both at the same time. When you run this recipe as a batch, you'll get black and white images saved for every step that you have set as a layer. And if you have global measurements in the recipe, you'll also get those measurements performed on every step that you have set as a layer and put into a spreadsheet. We'll see more of that as we get a little bit deeper. So what I want to just do now is clear this recipe out completely and just kind of demonstrate the actual building of this for this problem. If you were approaching this fresh and you hadn't looked at a pre-built recipe, and you felt you wanted to dive in and build it yourself, which most of our users do, I would probably say, well, my particles are overall pretty bright relative to their background. So let me start with a basic threshold under the segmentation menu, where I try to choose a threshold value that separates the particles from the background. I can start with the auto selection, which, if you're interested, uses Otsu's method of minimization of intraclass variance to automatically choose this value that, in the case of bimodal histograms, fits nicely between the two peaks. Let me also point out, you have your help button here for all of these preview windows that will take you directly to the relevant page in the user manual. And here we do discuss Otsu's method used for auto determination, and the reference is down here. So you're, of course, able to adjust this selection around here and find the proper threshold value. The auto selection works very well in this case, so I'm going to go with that. You also have this adjustment ability, so let's say that you're noticing that for a set of images you're working on, the auto is always off by about 20. Say putting an adjustment of 20 will have the software auto-calculate the threshold and then add 20 to it. So it's still a dynamic parameter, but you're giving a little bit of help with the adjustment. Not only does setting auto-calculate the value for this image, but when accepted, now this step is automatically recorded, that's how easy it is to build up a recipe. And with this step being auto, now the next time you ran this recipe, say on a different image, that auto calculation would be redone. That 153 is allowed to change image to image. So we've done a rough threshold, and we're noticing, okay, we've got some noise inside the matrix and inside the grains. So let's get rid of that as simply as we can. There's a couple of different ways. There's almost always multiple ways to process any image. Sometimes there's multiple ways to process or to conduct a single step. The simplest approach, in my opinion, would just be a couple of reject features. Reject white features, reject black features. So let's start with white. We'll go under cleanup and we'll click reject features. And I'm going to come in here and I'm going to say I don't want anything smaller than this passing through as eventually a particle. Right now the particles are empty, but once we invert this thing, then the particles will be selected. So let's get rid of these white holes so that they're not considered as particles at the end of the day. So you can type in a value here. You can see you can select or reject white or black features. Again, I say white or black because that's what they really are, is white or black. We're just looking at them in overlay mode. And you can reject features on the basis of any of these parameters. Area is the most common. Just reject features that are under 20 pixels, but you can also reject on the basis of eccentricity or aspect ratio, diameters, more advanced shape measurements, all kinds of options here. So we could trial and error what size to type in here, or we could just have MIPAR tell us. So just take your measurement tool, click on all the features you want to measure. I'm just going to double click that once. 35 pixels. So I'm just going to say get rid of white features that are 50 or less. And now they're gone. And you can preview that step on and off. White features are gone. Now let's do the same thing for black features. Come in here, 50. Black features are gone. So we've cleaned up the noise. We've gone from here to here to here. Now again, we've got a non-destructive recipe. So in principle, we could say, well, maybe now for some reason I'm thinking my threshold needs adjusting. I'm looking at my outline and it doesn't really need adjusting in this case, but suppose it did. You just click that step, hit edit, make a change to it, hit accept. The rest of the recipe gets automatically redone, and now it's all updated. You don't have to delete back your work. You don't have to be duplicating images. You don't have to be taking notes on what you've done. It's a non-destructive, flexible, customizable recipe. I'm going to set that back. Now, you can undo the last recipe edit. So if I just hit undo, then that last recipe edit gets undone. So we have now a particle or a matrix selection. What I want to do is flip this around now. So let's invert that. And I can add now a separate feature step that cuts all these particles. So let's go under morphology, separate features. And our recommended starting weakness for this is 3. The weaker the setting, the fewer separations you make. 3 seems to work pretty well for most cases. And there we've cut the particles along these lines. We've actually made one, I think, false cut right here. I don't believe that that should be cut. So we can take this up to something like 5, maybe 7. And now that cut goes away, but these other ones remain. So accept that, and now we've made our separations. And you can see the difference. If we go back to before we separated and we look at a labels view, the individual colors indicate separate features. So these are connected here, these are connected here, but after we separate, now these are split. And lastly, I'm then just going to invert this. Let me show it as overlay. So now I've got my nice, the other phase, the matrix selection. And setting them as layers is as easy as saying this step I want to call my matrix or my grains. And this step I want to call my matrix. Let's make it blue. So now we've got grains and matrix. Save your recipe and we are done. So now imagine that we had a different image entirely. So I don't, but if we did, take your recipe, drag it in, and there you go. So that's a pretty basic problem there. We've just got a few steps, some selection, some noise cleaning, some separating, and there we have our particles and matrix selected. Johan asked if we're going to talk about some optimization. I think yes, we will. I'll try to get into that in the advanced segmentation section. Our optimization for steps that are optimizable, which you can see a excellent question, Leslie. I was going to transition into that. Very, very insightful. Leslie asked pre-processing to remove noise versus reject features. That's she's right on. You obviously have plenty of experience because you're right on the money. Yeah, we'll get into optimization hopefully once we go into the advanced segmentation section. The optimizable steps, just as a heads up, are listed in the optimization section of the user manual. They include many of the common ones like thresholding and reject features. Well, I guess not reject features, but thresholding for sure. And what it does is it lets you say, I'm not sure what the parameter should be. I know that it should be somewhere in this range, and you let MIPAR try out the step at every value in the range, and you use a metric, usually mutual information, to compare the result of the step against some reference image, and MIPAR then chooses the parameter that maximizes the mutual information, otherwise known as image similarity, between the output of the processing step and the reference image. So real quick, on a basic threshold, it would look something like, I want to optimize my threshold value against the prior image, which is fine. We'll use the entire image here. And we say, I don't know, my threshold should be somewhere from 120 to 170 in steps of 1. So now it's running that loop. It's trying out the threshold at each one of those values. It's calculating this mutual information. That's interesting there. Why is that not changing? Huh. Oh, okay. It's because we have auto set. So, my mistake. With auto set, that is actually forcing it to do the auto calculation at every step. So it's coming up with 120 each time. That needs to be made a lot clearer. Apologies for that. Well, let me turn off the manual here and make sure. So I just put it back to manual instead of auto, and let's do a quick check here from 120 to 140. Okay. So there now it's vary the threshold as a function and calculate the mutual information for each. We need to expand our range. We'll clean up that issue here in the next release. Thanks for Johan for pointing that out. Yeah, so make sure you don't have auto set on a basic threshold step if you choose to optimize. But that's the idea, is that you let MIPAR vary the threshold value over a range and have the selection be automatically determined. So let's do it again over a proper range. Let's go from 145 to 165 in steps of 2. So you'll see mutual information vary as a function of threshold value, and then it chooses the so-called optimum one. Now, this doesn't always work perfectly. It's not magic. What it's telling you is what it thinks the best binary representation of the image is. So in this case, because you've got some darker blotches inside of the particles, using mutual information, it thinks that this is the best binary representation. So here's an example, Leslie, where you probably want to pre-process the image to eliminate the noise inside of the particles prior to optimizing on it, so that you're handing MIPAR a cleaned up interpretation of the raw image. I don't want to spend too much more time on optimizing right now. It's even more important when you look at particle boundaries and try to optimally select them without having any subjectivity. That can make a huge difference on the area fraction that you measure, and with MIPAR we have a way of objectively deciding where boundaries should be, so that you at least have numbers to fall back on as to why you drew them where they are. So I'll just finish up by demoing that. Let me unoptimize this and take us back to our auto value. Imagine at the end here, after our separate features, that we wanted to just grow all of our particles to make sure that, and I'd actually do that before the separate features, we want to grow all these boundaries to make sure that they're mathematically drawn in the right place, and that eroding or dilating by 1 pixel won't improve the selection. So if I do a dilate step here and I give it any old value, I mean, there's the dilation of 1 without the dilation of 1, and you could convince yourself that either one of those is accurate. So if I take the dilation step and I optimize it against the, let's compare the dilated particles against the original image, and I let the dilation depth vary from 0 to 5 in steps of 1, and it's going to come back and it's going to tell me that, well, at 0, thanks for pointing that out, Reagan. Actually, depth of 0 is better than a depth of 1. So this would give you evidence for not dilating the particles. And you'd probably, to do your due diligence, also want to put in a uniform erode step after of some value, and then optimize that as well, just to make sure that shrinking the particles doesn't produce a better segmentation. So we go from 0 all the way down, and again, no erosion is better than some erosion. So Now, with both of these steps in there and optimized, those calculations for growing and shrinking will get redone every time you run the recipe. So you've got a little bit of a check in here that your boundaries are mathematically in the best position. If you turn off the optimization, then you're basically burning in that value of 0 into the recipe. Whereas when they're optimized, their values are allowed to change because they're recalculated every time the recipe is run. So let me go back now and address Leslie's question a little bit better. She asked very insightfully, what about pre-processing the image so that you don't have any noise rejection? That is a very valid approach, and I can't say, in my opinion, that one is definitely better than the other. For some reason, my personal preference from my experience is to threshold as early on, as close to the original image as possible, and then clean up the thresholding noise. But it's definitely acceptable to get rid of the noise so that you don't have to clean it up from the threshold. And there are some cases where that's the only approach that works. In this case, I think either approach can work. If we wanted to see a pre-processing approach, then let's go up to the very top step and put in some pre-processing beforehand. We might do a median filter, and we'll say insert above. You'll notice that when you have the top step selected, you have the option to put the next step directly at the top. So we'll say above, and we'll come in here and pick maybe 5. So that kind of gives you a smoothing effect on the particles, helps get rid of some of this noise here. So accept that, and now that goes in place above the threshold. So now our threshold is much cleaner than it was before. We probably, ironically, well, maybe not. I mean, this black speck here is selected because it's very dark, so it's up to you. You may still want these reject feature steps to be in here because they still get rid of these small artifacts, but maybe we can at least get rid of the white reject features, since we can say that, or we can take it down in size and say that is a legitimate one that we want to keep, but this one isn't. So I can probably at least make an edit to the reject feature step, and here's a good case. These two here are 5 and 25. I'm not sure if this one is one that we'd want to keep. Perhaps it is, but maybe we could at least say if you're under 3 pixels, and we're going to get rid of you. So we reduced that from 50 to 3. The black ones, or the selection noise like this, we probably still want to keep in place, but maybe it too can also go down from, say, 50 to 10. And then we still need to invert, we still need to separate, and then we invert again to have the cleaned matrix selection. So that's how you can test. You can put some pre-processing up before you threshold, and then see if you still need as much of the noise cleaning as you thought that you did. But that's a very valid question. We also have some other options besides Wiener filter, or median filter, I should say. We have the Wiener filter, which is a more intelligent median filter. If I put that at the very top, you can see that at higher window sizes, edges are better preserved in the Wiener filter than in the median. So areas where you've got a lot of variance in the image, which down in here, you get less blurring in those high variance areas than you do with the median filter. Then we have our new non-local means filter, which is fantastic for noise rejection, but it can be a little bit process intensive depending on the size of your image and your computing power. I almost would never go above a window size of 4. You'll see the effect of this here. It's exponentially faster if you have images that are under 1,000 pixels. And that actually took quite a bit longer than it usually does. I think the screen share is slowing it down. But this gives a very nice smoothing with minimal edge disruption. This strength here controls the kind of the amount of blurring that happens. So you could probably get a nice clean from even going with a window size of 2 here, and using a strength of maybe 0.1 or 0.2. Also, I do think if you wanted to resize this image even smaller, that would be no problem. At the very top, we could just throw a resize step up here and probably take it all the way down to 600 by whatever keeps it the same aspect ratio. And then you'll see your non-local means filter will operate much more quickly. So we can go in here with a window size of 4. Oh, I'm sorry. I said above, so that actually put it prior to the resize image step. So cancel that. Resize image, non-local means below. And in this case, we could probably take the strength down so that we have less blurring, but hopefully decent cleaning still. And you see that does a pretty nice cleanup job and keeps your boundaries intact. And then we can take out the median filter. Hop into layers view. Now, because we've separated, we've shrunk the size of the pixels, I can adjust the separation strength here down a little bit. So that's one example of what I would consider basic segmentation. Let me load up a couple of other examples here that I have queued up. Here's a biological example where we have some leaf disease spots. So here's the recipe that we've made to find them. We're working with a color image in this case. Now you've noticed this is running an optimized dilation at the end of the recipe here to decide those boundaries. You notice every recipe step is either a grayscale image or a black and white. That doesn't mean that we can't handle color images. It just means that we need some channel operation steps in the image, in the recipe, to decide what of the color image to use to really get at the contrast of interest. So when you have a color image open, your reference image is, initially at least, the full color image, and you can switch into grayscale mode to give yourself what I call a channel operation playground. So your color image has 3 channels, red, green, and blue. The auto mode is what's used initially. Let me clear this recipe out so we can just see the building of this. So initially you have this auto grayscale conversion of the color image over here. That's the starting point for your recipe. We can have, though, the first step of the recipe be to use a different channel operation. So if you just wanted to keep the red layer, then you type in R over here, the blue channel, the green channel, or you can type in the word green, or you can even do arithmetic. You can do red minus green, and that nicely grabs all of the red objects from the image. So that's kind of how you just decide what channel operation to use, by playing around like that. And then my first recipe step is going to be, from the memory menu, a channel operation, red minus green, and now I've got my red spots nicely highlighted up. So I can do a basic threshold on this, use the auto value, invert it around, and there are my spots. Now here's where I might want to go and add a optimized dilation step. So let me say dilate uniform by some value, optimize it using the entire image against the in this case I want to optimize it probably against the contrast in this image. So if I set this image up as a memory image, then I can use it in my optimization. So I'm just going to click on this step and say set it as restore image 1. So now this is restore image 1. So when I go down here and I optimize my dilation using the entire image, I can say compare it against restore image 1. let the dilation go from 0 to 5. And actually, it wants to keep growing. So that might also be telling us that we could, instead of trying to optimize the dilation at the end, we could optimize the threshold. I'm surprised that the auto threshold wound up being so much under the... Oh, that's really interesting. That keeps going. Yeah, let's optimize the threshold instead. Let's come over here. So when you check the auto box for a basic threshold, what it's doing is the exact same thing as optimizing using intraclass variance. It's much faster to click the auto button than to optimize against intraclass variance. So it looks like maybe a mutual information optimization would work better here. They're similar in what they do, mutual information and intraclass variance minimization. We have some references for them in our documentation. Mutual information is supposedly a more robust way of judging image similarity, and it's what I prefer to use, but there are times when choosing interclass variance gives you a much more reasonable result. So I'm going to switch this over to manual so that I can try optimizing the threshold against mutual information here. And we're going to use restore image 1. So threshold from, let's say, 73 to 105. Sorry, other direction. It's deciding on the proper range here. This can also run more quickly if you turn off the display. So let me just let that finish and see if I need to extend the range further. I mean, of course, this is also, you have a more objectively determined threshold value. I think we'd be pretty able to set the threshold level ourselves manually down at. Let's unoptimize this. The threshold's probably going to want to be, I mean, really, it could be all the way down at 0. Honestly, that could be a decent boundary. So let's do that. Let's set that at 0, and then let's not add a optimized dilation. Let's add an optimized erosion, and see if we just need to shrink these at all. Okay, and it looks like we did hit a peak there. So right at 1, we maximize our rate. Really? Okay. Let's try from 0 to 3. Well, looks like 0 is going to be our best there. So a threshold of 0 gives us our best mutual information. So that's good to know. Well, there's our spot selection. Okay, that's a biological example there. We did have a submission for some white precipitates at the interface. I'm not sure if that individual is with us. I don't believe I see his name. We can circle back around to those, but I do want to move on to some additional examples. The advanced segmentation I don't foresee to be too challenging. I don't want to go crazy here for an introductory session, but hopefully you can see the flexibility and the power of MIPAR. Users have told us, and we believe you really don't need to be an expert to build up recipes like this. And once you have them, I mean, no, we don't have a button that you can click that says find disease spots, but you basically do just by virtue of being able to load in a recipe that you've made for your problem. So now every time you've got a leaf disease spots recipe, let's discard that, just load in your leaf spot recipe, and it's effectively as though you clicked a find spot button. So the efficiency, both in building recipes but especially applying them after they exist, is quite nice. Are there any questions at this point on anything that anyone has seen? Things that you had questions about or were hoping to see for the basic problems? Okay, I don't see any questions popping up. So let's move on to a submission that we had from Reagan. Thank you so much. Reagan submitted some examples of leaf fragments that he's working with. I can start with this example here. This is a nice kind of interdisciplinary example. Even though it's biological, it looks reminiscent of grains that a lot of us in material science encounter. So here's what Reagan supplied us with. A very nice cellular image of cells that need their boundaries traced inside of this region. So what I came up with, and I'll show you the building of it from scratch here, is a recipe for that. So if you, I'm gonna kind of now pretend that I'm doing this blind. I'm not gonna have any cheat sheet or anything over here, and I'll work you through the logic of building up a recipe for this kind of application. So it's a pretty high resolution image here. We've got 4,000 by 3,000. My feeling is I don't really need all of those pixels for this type of analysis. I don't think downsampling is it's still gonna leave plenty of pixels per feature, and there's enough uncertainty in the rest of image processing without worrying about whether you've got 1,000,000 or 10,000 pixels in one of these cells. So my first step was here to just resize this down to 1600 by whatever keeps it the same aspect ratio. Now what that does mean is I'm going to save a copy of this downsampled image here. This if I click save reference, I save the one on the left. If I click save image, I save the one on the right. So I'm going to save the downsampled colored image here, and just so that I can use it for calibration. Because this will be probably the first image that I'll take. I'll move right from this advanced segmentation example into making measurements, because this is a great example for that. Yes, thanks Leslie. Yes, you've got the size of the current working image up here in the properties panel. And let me also mention the view button. Clicking that will open up a table of your image metadata. This is pretty basic here because it's just a JPEG, but the proprietary formats that we can load with the bio formats often come with a wealth of metadata, and all those tags can be seen here in this table. We're also working on a cleaner way of, if your image does have a calibration factor in its tag, having that brought in automatically and notifying you of that. Right now, calibration factors that are present when a recipe is saved, they're saved into the recipe. But you can also save calibration factors as their own file. If you want a library of different cal factors for the different mags that you work in, you can build those up here in MIPAR. But using metadata a bit more intelligently and bringing in calibration factors when they exist in tags is something that we're working on. Okay, so we've resized the image, we've saved it so that we can calibrate, and let's go ahead and get started. So what I'm first going to do is just make a mask area, because I'm only going to want to be working inside of this space. So I'm just going to do that with a basic threshold. I can have that define my area of interest. So there's my selection. You look at it in black and white view, it's a little clearer. I'm going to do a reject features to just get rid of both the data bar here and the stray white spots. So I can probably just say 2000. I've got a pretty big size difference between this thing that I want to keep and everything else. This data bar is 2.5 grand, so let me actually just say 10,000. And then I'm going to do, instead of a reject black features, because in addition to getting rid of some of these, I want to just kind of smooth this out altogether. So I'm going to use the smart erosion for that. We call it a smart erosion because instead of just growing white pixels in all directions, it only turns pixels white if they're surrounded by enough other white pixels. So if I do smart erosion and I come in here, every pixel has 8 nearest neighbors, 4 on the faces and 4 on the corners. So if I chose a threshold here of 5, then I'm saying that in order for a pixel to be turned white, 5 or more of its 8 neighbors have to be white. So then I get a result like that. Excellent point there by Dirk. I'm so used to just doing basic threshold and inverting for problems like this that I forget that we have range threshold that can forego the inverting. So let's back out here actually, and instead of the basic threshold, let's do that, because we do want the bright areas, as Dirk pointed out. We can go into range threshold, and now you select what's ever in between the min and the max value. So that's a much wiser approach here. That way we don't have to invert after the basic. So there's a range threshold, and now we're going to do reject black features that are under 10 grand. And then we'll do a smart dilation to smooth this out. So if I do 5, then I get rid of empty pixels that have 5 or more of their neighbors filled in. If I were to do 6, that's a little bit more stringent because 6 or more of your neighbors have to be filled in order for you to get filled in. So you see you get a few less pixels changed. 4 is going to be much more liberal, and you're going to have more of a overall dilation take place. So I'm going to go with 5. And that'll clean up that boundary a little bit. So here now, I'm going to call this selection, whoop, not label, sorry, outline. This selection is going to be my, I'll put it as the companion image. And you can set that later if you forget to. I'm just setting it now because I know we'll need it. Now what are we going to do? Now we're going to go back to our resized image and start finding the boundaries inside of this region. So let me set a restore point right here. So I'm setting the resized image as the restore image 1, and now I'm calling it back. And now what I'm going to do is an adaptive threshold inside the selected area. So the adaptive threshold is actually our most commonly used threshold tool. Instead of your basic threshold where you're deciding whether a pixel is white or black based on whether it's above or below some absolute pixel value, you're assessing every pixel relative to its local surroundings. So you're asking not are you brighter than some pixel value, you're asking are you enough brighter than your local average is usually the stat that we use. So that would be your adaptive threshold here. You've got now 2 parameters, your window size and your threshold. We usually work in percentage mode, which would tell you if you keep a window size of 30 and you drag your percentage up here, under these conditions with white pixels as above in percentage mode, we're saying here that if you consider every pixel is considered 1 at a time. If you are less than 113% of your local average, then you're black. And if you're more than 113%, then you're white. If you switch this around, then you basically invert the situation. And now you have to be more than 113 in order to be black, or less than 113 in order to be white. So this works, I think, pretty well for this kind of microstructure where you've got varying contrast of your cell boundaries. The only thing I think I'm going to do is probably do a pre-processing on this to clean up some of this noise inside, and I'll probably use a Wiener filter for that. You could use non-local means, but well, let me choose a threshold and then insert the pre-processing above it, so you can see that workflow. So let's try 111. And now if I go back up before my threshold and I put in a Wiener filter step with maybe a size of 5, 7. Now the threshold is redone and I think is a lot cleaner. We could probably even go down a little bit and add some more selected pixels. You can also play with this window size here. Oh, that's actually really nice. Okay, now how to use the mask. So remember, we have in our companion image over here our area of interest. So right now we're thresholding the entire image. If I say set the companion image as the mask, now you're just thresholding inside of whatever features you had in the companion image. So there's that. And now let me just try to directly run a separate features on this to split up the cell boundaries. So let's try trusty old 3. You can make this a little thicker if you want to be able to see it more clearly. So I think it does a good job separating where it's supposed to. That's over separated, so let's try 5 instead. But we still end up making some cuts like this because of these holes in here. We do separate here accurately, but we don't want to cut through like that. So I'll accept that, because we can go, before we do the separate, we can go and add a reject features here to get rid of holes like this. We want to keep a hole. I don't even know if that's closed off. It might not be. Whoop. Yeah, it is actually. So we don't want to get rid of a hole that's this big, but we do want to get rid of ones that are that big. So orange is 307, red is 1809. So let's just say 500 or less. Now the reject features should, or separate features should not. It should avoid cutting through that because we've eliminated the holes there. And lastly, what I'm going to do is do a clean boundaries, which will grow every feature until there's just a nice thin 1 pixel boundary in between everything. It's like skeletonization, but it's a lot cleaner. You don't end up with spurs and branches that you have to worry about getting rid of. So that's under clean boundaries. Under morphology, I'm just going to use a thickness of 1, and that'll really just grow everything until there's a nice 1 pixel thin line between all the features. Now I do see there's a couple of little things like this that are then manifesting as these little noisy particles. So what I want to do is, before my clean boundaries goes into effect, let's add a reject features under separate, which will, I can probably just, I'm sure 200 is going to be more than enough. Now those should go away once you redo the clean boundaries. Lastly, we've expanded all the features out, and so they even expanded out into this space. But because we still have the companion image up here, right, where we have all of our AOI is black and everything else is white, that's the last companion image. So if I go down here, then I can add a merge lighter pixels step. That'll take the light pixels in this image, which are the white ones, and the light pixels in the last companion, and merge them together. So then we just get back, we erase everything outside the AOI. And now there's our cell boundary identification. We can look at it in labels view, which is kind of nice. Every cell gets a different color. You want to make quick measurements of a couple things. Hit my measure tool, wait for it to start up. I can pick these guys, and it'll give me just stats on each of those: red, green, and orange. All kinds of stuff. Usually not really what I'm after. I'm after a more global quantification of all the features, which we can easily do. That was the measure features tool that I clicked, by the way, for that. So if I took my cells here that I found, and again, let me save this guy here, and we'll just call it. Yeah, I can save over that. So imagine I've approached my problem. I have my recipe either built by me or sent by us. I'm gonna run those steps and find our cells. I'm gonna quickly just okay. There's a chance that you might want to get rid of the edge cells. It's not as simple as just doing remove edge features as would normally be the case, because this considers features that touch the edge of the image. If you did that, you'd get rid of features that touch the edge of the image, but we also want to get rid of ones that are here on the boundary. To do that, what you can do is take this image, and I'm going to set it as restore image 2. You've got 6 of those restore slots. Then let's go and bring back our companion image. So let's call companion. We're going to do a perimeter pixels off of that highlights the perimeter pixels as white. We're going to invert that around so that they're selected, so that we've got perimeter pixels here. And then I'm going to set this as the companion. And now bring back my cell image, restore image 2. So now what I can say is keep exclusive features, which is a new function introduced in, I think, 101. If we do math keep exclusive features, that's going to take all of the features in our current image and only keep the ones that do not touch a feature in the companion image, which is our marked edge. So if I say math keep exclusive features, now we're just keeping those that don't touch the edge pixels. So now we have here our fully contained cells inside of a non-rectangular AOI. So we can call this find full cells. Okay, these ones will measure, because these ones are not subject to edge effects. I don't know that, I'm not quite sure what metrics were of interest here. Probably cell size, I would say, at least, and maybe shape. You feel free to chime in, Reagan, if you've got more relevant metrics than what I'm playing with. If we just wanted to make measurements of the cells as a spreadsheet, well, let's calibrate first. So, well, I can show you what happens if you don't calibrate. So if we're showing the image we want to measure, we say measure features. Let's check off the area, the eccentricity, which if you hover over it says it describes how elongated it is. 0 is a circle, 1 is a straight line. Equivalent diameter, and I'm just going to call these measure. So that's going to make a measurement from every feature in the image. And now here in measure, if we open that in Excel, we have a spreadsheet of feature number area in pixels, eccentricity unitless, and equivalent diameter in pixels. If we calibrated our image, we would choose the image to use for calibration. So I'm going to take my resized one here. It's a color image, so it's automatically just displaying the first channel for this tool, but that's enough to see the scale bar. So let's zoom up there, drop our line down. We're working on, I know it's silly, we should have a shift for horizontal function, but we don't at the moment. So you can right click on it and say constrain to horizontal, so then it'll only drag perfectly horizontal. So let's drag this out and say that's 50 microns. So there's now our calibration factor. Now I thought I saw that said 20x up there, so if you want you could save this factor here as cal 20x, and then the next time you were working, if your image wasn't calibrated, just erase that factor out. You can just hit load and pick your cal factor from your library, and now you're calibrated. So now that we're calibrated, we have a number typed in here. I mean, if you know it also, you can just type it in. If it happens to be in your metadata tags, then you can just type it in. But once a number is typed in, we're calibrated. So now if we go again, measure by features, yes, Leslie asked, can you track the numbered feature measurement on the image with labels? I will show you the ways that we can do that here in just a moment. If we did area and eccentricity equivalent diameter, then we'll set this up again. I'm going to just call it as measure once more, close that out so it doesn't conflict. And now you see when we reopen this, everything's in microns. Okay, so we've got a spreadsheet of measurements. It's not very attractive. We don't have direct histogram plotting tools in MIPAR, but we're working on that. You're certainly welcome to use Excel or whatever other plotting software you like to use, Origin, Sigma Plot, Kaleidograph. Oh, you're very welcome, Reagan. Thank you. Shape parameters in general aspect ratio, nice. Yes, so aspect ratio is, I guess, not exactly eccentricity, Reagan, although they scale identically. We do have major and minor axis length as printouts, and I could show you that real quick. If you're heading out, feel free. I'm not trying to keep you here. Let's add those to the list. Let's do area, eccentricity, diameter, major and minor axis length. But you're correct. I think a direct aspect ratio box, even though it's kind of overlapping with eccentricity, would be nice. Yep, sorry, that's open. Okay, so we've regenerated those. What you could do is open these up in Excel like we did before. And aspect ratio would be, I'm not sure how you like to define it, maybe major over minor axis. Now let me resave this file. So, since we have generated measurements, we can come right up here to our color by measure tool, and we can load in that file. That brings us in all the measurements from that file here in the table. And then whatever measurement we want to visualize, just click any cell in that column. So if we want to visualize diameter, just click a cell in the diameter column, and now here are the cells colored according to size. Whatever row you have selected, that feature gets highlighted in the image, so you know exactly what feature 35 is. However, we have had requests for printing the feature numbers on the actual features, either in this window or in the image processor window, and we're working on adding that. It might get into the next version where you'll have little boxes that show what each feature is labeled as. I prefer this kind of visualization because it not only lets you see what feature you're highlighting, but also lets you color according to measurements. But I definitely get that sometimes you want to hand your boss a spreadsheet of numbers and a labels map. so that you don't have to be in the software to make the connections. Let me just read Johan's question here on line intercept from measurements versus line intercept from feature measurements. Okay, great question. So let me finish getting through the color by measurements window, and then I'll answer that question, Johan, because that's a good one. Let's say we want a color aspect ratio. Just pick a cell in that column. Here you see the elongated cells are very high, very yellow, and the rounder cells are blue. That's pretty cool. You'll see the same kind of trend here with eccentricity. But I do see now your point is definitely, Reagan, that even though the trends are kind of the same, I think aspect ratio is a little bit more sensitive to, because it doesn't have an upper limit. In theory, you could have an infinite aspect ratio, whereas eccentricity is only between 0 and 1. So yeah, we'll try to add a direct output for that. Right now, obviously the workaround is to get the major and minor axes and calculate it yourself in Excel and then load in the table. So that said, if we close out of this here, even if you haven't made a great question there too, Reagan. That's the $64,000 one, is how many changes does one need for different images. Let me quickly just jump back in here and show, if you have not made measurements before, you can make them directly in here, which is where having an aspect ratio check would be great. You would just pick off the measurements of interest, generate, and they would dump then immediately into the table over here so that you can color by them. And then of course you can export this table. If you wanted to export, add an aspect ratio column, read it back in, that can be done all within this interface. Let me quickly address your question, Reagan. It really depends. Simple recipes that don't have normalization steps in them, that don't have optimized steps in them, can need tweaking from image to image. It depends on how flexible the recipe is, and it depends on how much the images vary from one another. So looking at the two ones that you submitted, it would be tough to come up with one that worked for both this one and this one that you submitted here, because you've got much different backgrounds, different cell shapes, different intensities at the boundaries. I'd probably want a recipe for images that looked like this and a separate one for ones that looked like this. But even if you had overall contrast variations between two images that looked like this, we would probably put something like a auto contrast step underneath the resize step that would then hopefully normalize out variations that you saw image to image. We might want to do an optimization of a threshold step so that the recipe was flexible enough to accommodate changes. So in a perfect world, you have one recipe for all your problems, but it's not usually the case. You sometimes need separate ones for different problems, and sometimes you do need to tinker with steps. We've tried to make that as efficient as possible, but it can always get better, so we welcome any feedback on that. It really is a case-by-case situation as to how robust a given recipe can be for a given set of problems. But we have surprised ourselves. We have come across variations in images that can be handled with a single recipe, so we're happy to work with you on that. The goodness of the recipe, yes, fantastic question. Nothing as clear-cut as that, Leslie. We've shown, the optimization can be used to assess the goodness of a given step. As far as like a sensitivity analysis, that's not automated right now, but it would be nice if you could vary one step and say plot the resulting area fraction. It's going to be granular like that. Yeah, you're going to want to have. I mean, if you've got a ground truth of some kind that you're comparing the result of a recipe against, and your ground truth gives one area fraction and your recipe gives another, then the disparity between those could tell you the goodness of the recipe. We definitely welcome your suggestions on that, especially as an end user, because we are trying to long term down the roadmap find ways of assigning a score, so to speak, to a given recipe, but there's no canned tool for that at the moment. Johan, I want to get back to your question here. Your basic question on line intercept from measurements versus feature measurements. Yes. So from measurements here, you've got a set of intercepts functions that draw either a set of random lines or a grid of rotating lines along the through the features. So the ASTM grain size E112 standard is built in here to MIPAR, and it's done with the random lines function. I think that standard tends to specify 1,000 lines drawn through your sample in random orientations. You set up the intercepts parameters with the default settings and say accept, that's what it'll do. It'll run 1,000 random lines through the image, and then it prints out the average intercept length through the black, the average through the white, the average inverse length through the black and the white, the mode inverse and regular intercept lengths, but it's random lines drawn through the image. So we got 14.2 that time, but if we double click this and run it again on this same image, 14.2852, 14.0297. So you're getting different answers because you're running a grid of random lines. That is the variation between those instances are not to be considered as the confidence that you have in the precision of that measure, in the overall confidence that you've measured these features accurately. This variation is giving you an indication of the kind of the precision of the ruler that you're using for this one measurement. You could up the number of lines and then you'd have a more precise ruler. But if you were observing multiple cases of these cells from image to image, you're going to expect more of a variation from image to image than you would the sensitivity of the ruler that you're using. So it's sort of a precision versus accuracy argument. That's why we have the grid of rotating lines that puts the same lines down every time, so that if you ran your rotating lines you ran 1,000 rotating lines that are spaced evenly, starting from 0 degrees, so running horizontal, that then rotate through 180 degrees in increments of 10. That's running a grid of parallel lines and then rotating that grid from perfectly horizontal to the other horizontal. So they start at 0 and they come all the way around to 180. You then get a rose plot that shows you the average intercept length as a function of line orientation. So this is kind of a measurement of microstructural anisotropy. The more elongated this thing is in one direction, the more anisotropic your microstructure is. So this is pretty uniform. We give you an anisotropy factor, which is an aspect ratio of this shape right here. And now we get 14. And you'll see every time we ran it, we get the exact same number because we're using the same grid of lines every time. So if you don't want to have to explain why you might get different answers when you put down a different grid of lines, you have the rotating at your disposal. But those are all rotating. Those are all random lines drawn through the microstructure, either completely random or a rotating grid. The measure features lines here are done on a per feature basis. So if we took intercepts measurements with a given number of lines, we can either run 100 random lines through every feature, or if we then pick this, we can force them to all run through the centroid of the feature, so that you're then outputting the average intercept distance by running all the lines through the centroid. So could be thought of as a a more advanced diameter measurement than just equivalent diameter. So equivalent diameter takes and gives you the diameter of each feature if that feature was a circle of the same area. And that works well for circular-ish shapes, but if you want to measure the diameter of an elongated feature, which when you think about it, boiling down an elongated feature's size to a single scalar starts to lose meaning anyway, but if you did want to assign one scalar to the size of that feature other than equivalent diameter or area, one option could be run 100 lines through the centroid of that feature randomly, but all passing through the centroid, and the average of those 100 lines would kind of be an average diameter through that feature. We also have Ferret's diameter. That's the largest line length that fits inside that feature. So that's the difference between feature measurements, intercepts, and global intercepts. Global intercepts, a bunch of lines in one image, randomly or rotating. Feature intercepts, a bunch of lines through every feature, either pinned to the centroid or completely random. So there are some measurements. Any measurements that are put in the recipe get put in the recipe. So when you run the recipe, in addition to detecting features, you also run the measurements. If you ran this recipe as a batch, then again, in addition to with no layers, you would get the binary last image saved of the recipe from a batch process, and then you would get a spreadsheet of measurements made on each image. We tend to not put measurements in recipes for a batch process. We will just have the recipe do the feature detection, and then after the batch is run, open the results in the Purple application to do the review and the bulk measurement export. And I'll show that once we hit the batch processing segment. So those are some measurements there. We can jump into let me show you this bimodal example here. So let me take the take this image here. This is a picture of asphalt where we've got two different particle size populations, and we've made this recipe here for their detection. A few steps. I can try to build something up quickly and more simply for this kind of problem, but it's going to involve some thresholding and some noise cleaning and some separating and some memory steps to discriminate between the fine and the large particles. I'll work through this problem here real quickly and see what we can get from scratch. So let's just start with a basic threshold here for the large particle finding, and we'll go actually and use Dirk's suggestion here of, now the one advantage of the basic is that you have an auto button. We probably should put an auto button in here for the range threshold, but that is one primary difference. So there we've selected the particles. What I'm going to do is erase the smaller ones and find them with a better technique and add them back in, and then do the sorting between the two types. So let's first do some smart dilation to clean up some of the peripheral noise around here. It's going to be dilate smart, and I'm going to say zoom in here. Let's try 5 for the threshold. Then we can do some hole filling, so we'll reject white features. Let's give a rough size scale estimate. That's 200 pixels. You can do true hole filling, which is just getting rid of any hole that doesn't touch the edge of the image. If I said target white features, ignore the edge ones, and get rid of anything that's under infinity, that's hole filling. You're now getting rid of all white holes that don't touch the edge. That could be risky because sometimes you've got a massive landlocked white feature that you don't even know is there until you remove it. So I tend to prefer to just keep, consider all edge white features and just work with finite size cutoffs. But true hole filling is there in the form of ignoring the edge features and setting infinity as your upper limit. And then what we're going to do is get rid of small ones. Doesn't really matter what we pick here. We're just trying to target ones that are not nicely found with a global threshold, because you've got such a refined particle dispersion in here that's got varying contrast. This calls for an adaptive threshold kind of an approach. We'll save the global for the big ones, and then we'll target the small ones with the adaptive. So let's just get rid of, how big is that one there? 500 pixels. Let's say 1,000. So we'll dump all the small ones. Maybe we'll keep some of these bigger ones here. So say 500. So there's our bigger ones kind of found. I'm going to tuck that away as the companion, and we're then going to go back to the original. And now I'm going to do an adaptive threshold on the original to go after the small ones. Let's try. Your window size is usually dictated by the scale of the features of interest. So if I pick a distance line here, I see, well, that's about 20 pixels across. That's about 20. This finer one is just about 5. So somewhere between 5 and 20 is probably going to be my ideal window size. Let's drag your percentage up. Here's where you could use an optimization to pick the threshold in a region of interest. So I'm going to say I'm happy with 15, but I want to let the percentage vary and let MIPAR decide the percentage. So I can come down here and I can optimize using a subregion against the prior image. It says pick a subregion, so I'm just going to pick this little window in here. Double click on the edge of the box when finished. And I'm going to let the threshold go from 90 to 130. And it says 99 is my peak. So I'll go with 99. I'm not going to save that as an optimized step because I'm just assuming that I'm processing the same image type every time. I'm going to use 99 now going forward. I just needed MIPAR to decide it for me. And now we're going to flip this around. Let's get rid of features that are just under 5 pixels. Maybe just 2 pixels. I'd say if you're 2 pixels or less, I'm not going to count you a particle. And now we can add the companion image, which was our chunkier ones, to this state of the recipe just by doing a merge darker. So there we have, this was what we had before we did any of the combinative approach. We've got all the particle, or we've got the bigger ones nicely found or reasonably found with the range threshold. We've eliminated all the small ones here and filled in the big ones holes. Then we have down here, we've found the larger ones are terrible, but the small ones are good. So we're just going to fuse this image with this image to give us this. Now I'm going to run actually I'm going to do a separate, two separate features, because I'm going to target the big ones a little bit differently than the smaller ones. So here we have, before we set this up as companion, right underneath the reject feature step, let's add a separate features. Let's try 5. Let's look at outline mode. So that cut probably shouldn't be made. This cut shouldn't be made. So let's move this up to 7. And not 30. 9. 12. My bad. Well, we might just have to live with that artificial separation. But the rest of these got separated pretty well. There's a couple other separation approaches that we can go with, but let me just finish off this recipe here. So we've separated those with that step and set this up now as the companion. And now we're down here where we have the finer ones, and I'm going to go after them probably with a different weakness setting than we did the bigger ones. So let's try 2. Maybe even 0.7. Usually finer features like this need finer much higher strength separation values. This one's getting cut because of this spec here. So before I put that in place, although I could add it after, as we know, I'm just going to get rid of white features that are under 2 pixels. And then I'm going to add separate features here of 0.5. Now it splits all this up, but that doesn't matter because we're just going to cover over it with the other particles. So now I've got separated large ones, separated small ones in the same image. So this is all of my particles. And I can now do some sorting. So let's first just reject. I got to decide what I want my cutoff to be. So I could make a quick histogram and see what the cutoff should be, which is why histogram plotting tools we know would be nice in MIPAR. But I'm just going to kind of eyeball it right now and say this is my smallest coarse particle, and this guy is 664 pixels. Let's make 700 the cutoff. If your image is calibrated, you can do these rejections in physical units of microns, not just pixels. So we've gotten rid of 700, so here's our coarse ones. And I now need to recall this image to keep features under 700. So let's throw, you don't have to be looking at this to add a step underneath it. We can click that and add a restore image 1 step here. So now we can call that. So we've set up this image as restore image 1. We've rejected features under 700. We've called it back, and now we're going to keep features under 700. So there's fine, there's coarse. Take your coarse ones, set them up as one layer. Take your fine ones, set them up as another layer. And then we've got a bimodal segmentation. And you can, of course, we could make, when you're in layers mode and you went into color by measure or anything else that targets one specific image, it'll ask you, do you want to use the coarse or the fine layer? So if we said fine, and we then wanted to do a size analysis, let's do equivalent diameter. Got several thousand features, I would imagine, so let's just let those generate. Okay, and yeah, 9,000 features. Well, I may have wanted to do a underneath this merge darker pixels, I could add a reject features of like, I probably want to do another reject features of, actually I wouldn't need to do this black reject features of 2. I'd probably want to move this step down underneath the merge darker pixels, so I would reject the features under 2 after I did the separation, because it's possible that the separation induced additional features under 2 pixels that are responsible for this high feature count. But I won't worry about that now. There's no way right now just to drag steps around the recipe, so it would be a remove this step and then insert underneath merge darker pixels another reject features under 2. But let me click that cell and color. We sped that up dramatically. Usually for 9,000 features that would have taken a long time to color, but it's a lot faster now. And there we have our small features colored according to size. Here's a case where I think adding feature ID labels would not make much sense. You wouldn't want 9,000 numbers peppering this image. Here's where visualizing on a color scale is a little bit nicer. But like I said, we're going to try to get the feature ID labeling here added as soon as we can. Area fraction, I just wanted to use this image to demo area fractions. So once you've got your layers set, we can just do a quick area fraction measurement. And it's going to prepare those up and make us area fraction measurements of both layers. 34% of the image is, or 35 is coarse, 24 is fine. You could also do feature counts per layer, so we could do number of features. And we've got 71 coarse particles and 9,000 fine particles. Once you have a population of measurements down here, if you wanted to generate all of them again at once, if you're looking at a current step and you hit this one here, I'm sorry the colors are gone too. It switched my color scheme for the screen sharing, so these actually do have colors. They're not black and white. But generate report will conduct all of these measurements on whatever image you're looking at, or on both layers if you're in layers mode. So if I hit generate report now, it's going to make those 2 measurements on both layers. Maria asked, is it possible to segment particles in RGB images separately in each channel and then determine the co-localization of particles? Yes, absolutely. I believe we might even have a couple examples of that up on the recipe store, but that is completely possible. So you're going to have your color image loaded. You're going to start off with, say, just keeping the red channel, find your red features, then put that in memory, let's say, then do a green channel operation to bring the green channel forward, find your green features, and then between memory images and math operations you can do subtractions of the 2 different feature types to get an area of co-localization, let's say. I'd be happy to demo that for you if you have an image that is relevant to you. If you wanted to send that to me, I can get your recipe back, or you could register for a one-on-one training and we could work through that live. But we have done that for many other users. Are there any questions at this point on anything that I've showed? We're about just under 2 hours in, so I wanted to break off and probably move on to some batch processing, unless there were some questions or other segmentation cases that people were hoping to see. So let me open it up now. Any questions from anybody? Great. Okay. Well, hopefully that's a positive thing. Awesome. Thanks, Leslie. Thanks, Dirk. So, Let's move on to some batch processing. So for this, I'm going to show you I use this set quite a bit. We've got a few different images of a bimodal microstructure. Gamma prime is the name of these particles, and we call these larger ones secondary and these smaller ones tertiary. So that's the reason for the terminology you'll see. Let me just show you the recipe that I've made here. By the way, I just wanted to mention I should probably repost this up on the recipe store, because I think the one that we just made here live is about half the size of the one on the store. So I guess it's kind of like remodeling a home. Sometimes you just have to gut it and start over, and once you've done it once, the next time you do it, it's a lot more efficient. So just something I noted. Okay, we're looking at remodeling. We're looking at the gamma prime. So let's drag in this one here, clear the recipe out, and take our tertiary and secondary with layers recipe. So here we've just found the two different populations. As here we have secondary, here we have tertiary. We're in layers mode here. You can also show this as colored outlines instead of overlays. Sometimes that's a nicer way to show two different layers. You can also show and hide layers, I should have mentioned. So on a step that is, when you're not in layers mode, this button here, disable here down, will take this part of the recipe and temporarily turn it off. That lets you make changes and edits up here, and then the recipe is only going to update up to this point. So if you want to be messing around with step order and parameters but don't want to wait for the rest of the recipe to update, temporarily turn it off, make your changes up here, and then you can click on the last step that you want to enable, and now this button, instead of disable here up, is enable here up. So that'll then turn on all the steps that have been disabled and update them in accordance with what's been done above them. But when you're in layers mode, this button is hide or show layer. So if you, it's off when you're not selected on a layer step, of course, but if you want to show and hide the tertiary, you can do that without having to remove the layer. Just wanted to mention that. So we have overlay, we have outline for layers view, right. So let's take our recipe now and show some batch processing. So if you've saved your last recipe state, which we have because we've loaded it in and haven't made any changes, if you launch your batch processor, I guess we actually had, because we did some changes with it, we actually have, I guess, because we did the enabling or the disabling and re-enabling, MIPAR thinks we've made changes. So let me just say yes, resave this recipe. So it'll force you to save it if you never have, and then it will take that recipe and load it directly into the batch processor for you. Or if you just wanted to start fresh, launch your batch processor, take your recipe, which is this one here, drag it in, and you're set. Now we're going to take the rest of these images here, take all of those, drag them in. It will then auto set our going on here. Something is wrong. I knew I couldn't make it through one live webinar without some kind of glitch. Sorry about that. Let's chalk it up to screen recording. That's always a good one. And let me just kill my part here and reopen it for you. Apologies. Let me also take this opportunity. Okay, so we are in our batch processor. We're going to take our measurement, or our recipe, and the images. Quick little shortcut: if you just want to quickly see what this image is, double click it, and that'll spit it out into an image viewer. It automatically set the save directory as the parent directory of these images, but you can set this before you add images, or we can change it now. And then the auto suffix is processed, but that can be changed. So these images will get a processed suffix, and you'll also get a processed folder, or a folder with the same name as the suffix, inside of this parent directory that will contain all the processed results. So that's all I'm going to do. Recipe, images, go. And now we're running that on all 5. So let's wait for that to crunch through. So what we have now, if we look in our, so there already was a processed folder in this directory, so it made a processed 01. And if we go in here, you'll see we've got processed and then secondary and tertiary for every image. So every step that was set as a layer kicks out a binary segmentation at that point. Ignore the black lines. I can't seem to get Windows to not display black and white images without those, but they're not actually in the image. It's just a display artifact. So we've got secondary and tertiary for every image here. Now you can manually load all these. I'm sorry, I'm just reading Dirk's question here. Yes, so let me double check with Reagan offline that it's okay to share that cell recipe, and if it is, then I'll gladly post that up to the store, but permission pending. So we can load all these segmentations up into the processed image editor if we wanted to, or it's much more convenient just from the batch. Once it's done, hit review processed images. That will gather up all of the processed images that you just saw, load them into the right places, load in the right reference images, and now we have that. So here's what is actually loaded. We've got the tertiary layer. These are the black and white images for the tertiary, and the secondary black and white images for each. But of course, it's nicer to look at overlay. So here we've got the secondary images overlaid for each one. Do outline instead, switch to tertiary, or it's probably even nicer to go in the layers view, outline, and now you can flip through each one and see how your batch did. I'm not going to spend really much time on manual editing. Hopefully it's not necessary, but it's there if it is. Sometimes it's easier to just, instead of spending more time than you have to make a fully automated recipe, if there's just a couple of mistakes that you want to fix, like let's say you didn't want these features in here. These are in the secondary layer, so switch that to your active layer, and then you can use your select tool here, double click the last one, click the features you don't want and hit enter, or click and double click the last one and then say erase, and that'll erase those out. Now it freezes you from advancing to another image. You could type in another image number, or you could double click that image here, but it's going to warn you that if you do that, you're going to lose your changes that you haven't saved. So either click save and then you'll advance, or hit save here and then your slider bar is opened back up again. because again, it's reading these images off of the hard drive up here, so you're burning those changes to that image now. So now this is a manually manually edited version of the batch output. You also have the option to save as, so you can give the manually edited ones new names if you wanted to distinguish between edited and fully automated. You can freehand in ones that you've missed if you want to. If you did in fact want that one added, freehand and hit fill. So minor errors can be easily corrected with the manual editing. If there were separations that needed to be made that weren't, say up here you actually wanted these to be separated, you could take your pen tool and drag in here and say erase, and that'll make those separations. So it's a batch review environment that lets you switch through each image, make the manual edits if needed. Let me demonstrate one case where maybe this image just did not process very well. You can take this reference image and open it, so this will open that in the image processor. So let's wait for that to launch because it wasn't. If you have a recipe loaded, then it's going to ask, do you want to reload the current recipe on this opening image? And you would probably say yes to have your batch recipe that you just ran reloaded, but we didn't have that in this case. So let's come back here and drag in our recipe that we ran. So that recipe will get reloaded on this image, and let's say for some reason we needed to make a change, like we needed a different adaptive threshold on this one image. So we would do that and tune that up, let everything repeat. And now the two things that we need to save are the two binary images back to their processed location. We're working on even better integrating the processed image editor with the image processor so that you could have like a one-click button that would resave your processed results to the right location so that they are refreshed in this app. But for right now, it's going to be a go to black and white view, take your tertiary image, save it. This is I-4520, so I-4520 tertiary. Replace that. Go to your secondary, save, I-45 secondary, replace that. And now when you come back in here to your processed image editor and you hit refresh, that's the new version that just got processed from the recipe. So there's some communication between the two apps that lets you rerun a separate recipe on just some of the images. That can usually, if an image is just terribly segmented, it's advisable to revise its recipe rather than manually fix all of those things. But it's a case-by-case thing. So let's say that we're happy with all these segmentations and we want to export bulk measurements. So if we wanted area fractions of everything, you make those on a per layer basis. So if we wanted, let me switch just to overlay so that it's clear what we're making the measurements from. So I'll make secondary area fraction measurements, check area fraction, hit generate. These are area frac secondary. So it's measured those, and then we also want to measure area fraction tertiary. So now in this folder we've got these two. So area fraction for each of the tertiary selections, and the same for the secondary. That's bulk global measurement exporting. If you wanted feature by feature measurements made for every image, say you wanted the particle sizes from each image. Take and go and hit feature measurements, pick off the ones you want, save those to diams. So now it's going to make diameter measurements from every particle from every image, and you'll get one big spreadsheet with all of those in there. We had headings added, so use headings for each image was checked, so that's going to put stop points in your diameters spreadsheet. So let's open up the diameter spreadsheet, and you'll see here's the first image, all of its features and its diameters and their diameters. Here's the second image, all of the features and their diameters. We didn't have a factor in here, so it made everything in pixels. It's still just one global calibration factor for the entire application. We have had requests to allow for different calibration factors per image, and that is on the roadmap. So we'll try to get that added as soon as we can, so that you could hypothetically have different magnifications quantified from the same batch. Right now it is just a global factor for every processed image. If you didn't check headings, then all of these stop points would go away, and you just get two big long columns that would have all of the features from all of the images in one long column, so that you could make a large spreadsheet or a large a histogram from all the features combined from all the images. Tony asked, can we export to JSON format? And right now, no, we cannot. TXT and CSV are our two export formats, but I will relay that, and we'll add that to the roadmap. That's a good feature. No one's actually asked that before, but thank you for that. We'll try to get that added. Okay, so we've got the bulk measurements there. There's no bulk coloring by measurements or anything like that. It would be a case where if you did want to color a single feature, a single image, or if you wanted to color one of these images by measurements, we would advise taking the processed image here and opening it in the batch processor, and then you can go right in and do your color by measure on this one image. But we also do have a little bit ways down the roadmap trying to work in some sort of slider into this color by measure tool, so that you could bulk color by measure and export multiple images. So that is batch review and quantifying. It is back in the measurements category, not so much in the batch, but I realized I overlooked local measurements, so I did want to demo that for anyone who is interested. Did we have any questions or things you were hoping to see with regard to batch processing and batch quantifying? Okay. Tony asks, do we have a measure to match with a baseline? How far or close you are from it? No, I don't think so. Yeah. So sort of like a data analytics of your exported quantification. Ironically, we do have a data analytics app that's also way down the roadmap, where we would hope to start to be able to do things like pattern recognition and relationship fitting and extraction from quantification. But right now, no, we don't have any canned tools for baseline comparison. It would be something that you would need to plot out from your, say, plot the image to image area fraction or whatever it is that you're after, and use those kind of plotting tools to visualize any variations from image to image. but we do see a need for more data analytics inside of MIPAR, not just histogram plotting, but also that kind of pattern recognition and visualization. So thanks for bringing that up, Tony. Local measurements would be something like, oh, sorry about that. Let's open back up well, that's interesting. Make a note of that one. Let's open up. When in doubt, dragging in is a helpful way to open images. Let's drag in, let's take this recipe and well, that's a good time for me to mention that. So I reloaded the recipe so that I would have the reference image there, but if you did just have your processed image loaded and you wanted to put a reference over here, you can do that either with File, Load Reference, or click the Load button here, and then we can bring in the corresponding reference image. That's I-49, and now you have that there to do your overlays and so on. So you can have processed images just directly loaded in and still be able to outline and overlay them. So local measurements would be something like an area fraction map, or a density map, some folks call it. Into your local measure tool, area fraction is the first measurement. There's just really one parameter, which is your window size. So if you hit show window size, you can see what window you're using. Let's do something like this. So what this would do is it's going to slide this window across every pixel in the image and calculate the area fraction inside of this window for every pixel in the image, and then put all that on a color scale. So if we hit generate, now we get, here's the area fraction for every pixel in the image. And if I click a cell in this column now, here is the local area fraction of the particles plotted over the image. So a little bit of a higher local area fraction over here than over here. And we do have line profiling tools, so you can take and draw a line across there, and you can see that variation. Thickness is better demonstrated on a different kind of image than these particles, so let me close out of this and open up. Yeah, that's interesting. I guess we've got an issue from opening an image after you've directly loaded it from the batch processor, so apologies for that. Dragging in still works for opening images. Let's go down here to one of my plate-like feature images where we can show local thickness, and let's load in this recipe. So we have the plates and the background, and if I take my plate features and I do a local measurement of them, then we can switch to thickness, which will give us now a skeletonization method and a trim threshold. It's auto done the Maria asked about unbiased sampling, like for stereology, so I will go back and address that after I show this local thickness tool. So it's auto done the skeleton here. We've got, if you check it, you can see what it's done. The advanced method usually adds fewer branches and spurs than the classic, but sometimes you still do need to add a trim threshold to get rid of branches like this. What it's going to do ultimately is calculate the thickness of every pixel that lies along this skeleton line, and then kind of smear those thickness values out in order to colorize the rest of the features. But it's actually only taking the measurements at each point on the skeleton, and it's doing it by calculating the largest circle that fits inside the feature centered around every pixel along this skeleton. So your skeleton is really what you want, is where the data is coming from, so you want to make sure that you're only measuring where you intend. So if I bump the trim threshold up to like 20, then that'll start to get rid of some of these branches that we don't want. Maybe we do 40 instead. You can switch to classic and try the trim threshold too. Okay, I think maybe classic with 20 is what we're after. So now with my skeleton set, I can hit generate, and now you're getting, so this is just the pixel ID number. It's not very important, but these are all the pixels that fall on the skeleton. We've got a thickness value for each. So you can export this to export the table. Once we've visualized it, you can also export average values per feature, min values, max values, standard deviations, other things. But if I want to colorize, again, I'm just going to click a cell in the column, and let's hide the skeleton. So now this is a local thickness map of the features in the image. So locally thicker in the yellower and orange areas, and thinner in the blue areas. Keep in mind, though, that this is in fact a 3D microstructure. So this kind of leads us into Maria's question, that in actuality, these call them laths, I don't mean to use strange terminology, these strips, these are in fact plates in 3D. So these might just be thicker in this one two-dimensional cross-section that we've taken through the microstructure, and they could just be inclined relative to the imaging plane, and these thinner ones could just be more perpendicular relative to the imaging plane. So that is the essence of stereology, in that you acquire enough random cross-sections through your microstructure such that you can make unbiased measurements of things like area fraction and size, which is why we almost always acquire multiple images per microstructure. So there's plenty of work out there and plenty of studies that you can do, that we have done for different cases, for different measurements of interest. Taking one image and trying to make accurate uncertainty estimates from it is what we have found really not the way to go. If you wanted to make some kind of uncertainty measurement from, say, area fraction, then we would advise at least taking 5 images of your microstructure. You make your 5 area fraction measurements, and then you can do things like bootstrapping analysis, or even something as simple as a standard error on those 5 to get an error bar on that area fraction analysis. Now, prior to digital image analysis, prior to computational computer-aided image analysis, it was the norm to take your microstructure, your micrograph here, and put down either a regular or a random grid of 10 by 10 points, and something like this. So let's say you have let's clear this out. We can emulate that here. So if I make a blank image, and then I come down here and do a sparsely sampled image, I can take and only sample 5% of my image here as white pixels. So then let me invert this now. And now, I'm showing this as an outline here. These are several random points. Let's do just 1%. We could also do a regular grid. Let me change this to grid, and I could do a step size of 200 and 200. And I'm going to dilate this grid now just by a couple of pixels so that I can see. Oh, I don't need to invert it in that case. Let me take that sparsely sampled grid and okay, that is another issue that we need to take care of here. The sparsely sampled grid is being seen as a grayscale image for some reason. We can just threshold on it to work around that. Sorry about that. And then we're going to dilate these points just a little bit. So there's a grid now that you've overlaid, and what they would usually do is every time this point would hit a feature, they would count it. If it landed on the edge, they'd count it as half, and if it missed, they'd count it as a miss, a 0. And you could then say the number of hits divided by the number of points is your area fraction. And our understanding is that that worked well with the laws of stereology, because you just do that counting on one image, and you'd recognize that the certainty of that measurement was limited by the number of points that you laid down. In this case, you really could know your area fraction no better than 1 divided by the number of points that you had. So some have asked us, when you're doing computer-aided analysis now, should you be point counting your segmentation for area fraction analysis, let's say, or should you just be counting all of the pixels of your segmentation to do your area fraction analysis? And we could be mistaken, but my thinking of point counting a segmentation is much like especially if you're going to take multiple images and you're going to have the uncertainty be the variation from image to image, then it really doesn't make sense to me to point count a segmentation, because you can already view a digital representation of your microstructure as just a very dense point count. Every pixel of your image is a point that you've laid down on the microstructure, and your segmentation is telling you what points are hits and what points are misses. So to point count a segmentation is sort of to force yourself to use, say, a plastic ruler to measure your image instead of a caliper. You could use all of the pixels in your image, and when you then, well, exactly, when you repeat that over multiple images, you now have 5 caliper measurements instead of 5 plastic ruler measurements. The uncertainty of your measurements is really going to come from how many cross sections you've captured. The biasness of your measurements is going to be how many images you've incorporated into your quantification. So I would rather have 5 densely measured images rather than 5 coarsely measured images, because you're obviously going to get a greater uncertainty from your 5 coarsely measured images, but now you've convoluted the uncertainty that you've added from only using 100 points instead of all of the pixels with the actual variation image to image. But these are just some of our thoughts that we've come across. And some folks still prefer to take one image and point count in the segmentation with 100 points, and then repeat that random point count on the image 100 times, and say the uncertainty now of their area fraction is the spread that they get from those 100 measurements of the same image. And that's, if that's the approach that you want to take, then that's certainly okay. We're here to facilitate the different research approaches that you want to take. So what you can do is set up these point grids to do that kind of analysis. So I can quickly demo that here. Let me load back in my recipe that I have for first segmenting this. What's going on here? So if you wanted to measure the area fraction of just these strip features, let's turn this off as a layer. We just need so here's our end selection where we have all of the features of interest selected. I'm going to put this as companion and then go and do my grid setup. So here's a blank grid, sparsely sampled. We're going to use a grid of 50 by, or a step size of 50 pixels in between. Work around this issue of it being a grayscale image here. And then let's Actually, just let's not dilate here. So now if I look at, here's all of my points that have been laid down, and if I do a merge lighter, then I will only keep the ones that hit. And if I save this as restore image 1, then from here I can bring it back, and let me actually, before I bring it back, let me call the companion image, invert it around, reset this as the companion, call the restore image back, and do another merge lighter, and now these are the misses. So we can call these misses, and we can call these the hits. So the green ones have hit our segmentation and the red ones have missed our segmentation. And if you did a number of features count of your 2 layers here, then we could also add this here as the total. So these are all of the points. Now let's rerun number of features on all the layers. So we have total points, hits, and misses. And that's a way that you could set up a point counting stereological experiment. You also asked about Z dimensions, Maria, so that's probably going to take us into 3D analysis. In principle, I mean, if you take a polished sample and you've cross-sectioned through a random microstructure, then you have effectively observed you've observed a nearly infinite number of cross-sections through a 3D microstructure, so there is some Z-dimension contribution inherently in any 2D cross-section through a 3D microstructure. I'm not sure if that's what you meant, but from setting up these point grids and then using them to count your segmentation, I suppose then you do have a way into some unbiased quantification. So that's kind of taken us back now through some other measurements. We showed local measuring. We showed some point count measuring. We had finished with the batch processing, and that just leaves, okay, so is for the case of Z-stacks of confocal images. Well, we can work with Z-stacks to make reconstructions, and we can do random line intersections through those 3D reconstructions. I don't know that we can do 3D point counting out of reconstructions yet, but we can export random cross sections through a 3D reconstruction back out into images that you could then point count. I'd probably recommend we have a custom session to show some of those tools. Is there anyone around here that wants to see 3D analysis of one example data set? Or do we want to open it up to more questions and close out? Okay. Rightly put, Tony. Looks like we don't have any 3D interest, which is totally fine. MIPAR is shown to be more of a 2D analysis tool for folks. I'd say 90% of our user base just uses the 2D stuff. And we do actually have a collaboration going with FEI, who's now the parent company of Aviso 3D software, which I think is one of the best out there. We're collaborating to help them add some of MIPAR's recipe building features into Aviso to make 3D segmentation easier. And it is possible that somewhere down our lifetime, possibly in the next couple of years, the 3D side of MIPAR may go away, and it'll be a dedicated 2D analysis platform, and we'll be encouraging folks to look at the MIPAR inspired extension into Aviso. Just wanted to throw that tidbit of future news out there. Well, we're about just over 2.5 hours in. We've covered quite a bit of ground. I think I had a couple other advanced segmentation examples in the pipeline that I didn't demo, but I can load those in here if we want to see anything. So let me just clear out this guy, and here's a grain structure that we have, and we can, with a few steps, whoa, definitely not that one. These were test cases that I had made. Apologies. Here was the recipe for this image here. So we can do grain boundary finding from images like this. Grain size, measurements, of course. Colored by size. And again, if you want to see a nice overview of the different application examples, the About page on our website and the recipe store has some good ones. Do we have any last minute questions before we close out? I can stay around as long as anyone needs. Doesn't look like much. Thanks everyone for attending. Feel free to hit me up by email afterwards if you had any comments or questions that didn't get answered. We will try to make these a little bit more regular and possibly a little bit more specific depending on the number of attendees. Thanks a lot, Tony. And we'll send you all a link to this recording once it has been posted. Thank you so much, and I look forward to speaking to hopefully each of you later on. So this will close out the third webinar, and please visit us at MIPAR.us and contact us at support at MIPAR.us anytime. Thank you all.